Hello everyone, welcome to Bright Minds Academy Goa. This classes will be for Goa Board Class 12th Mathematics. We are starting today with Chapter 1 Relations and Functions. So this here is the syllabus for relations and functions. First we're going to look at the different types of relations. We're going to have a look at reflexive relations, symmetric, transitive, how they are different, how to identify them, what's an equivalence relation. We're going to learn all about this. Then we'll hop on to functions. We'll learn what is a one-one function, what is onto function. Then we're going to learn about composite functions, and lastly inverse of a function. So we're going to start with the very first topic here, which is relations. I'm going to first go on to relations and then we're going to learn about the different types of relations. So if I say that I have a relation from set A, that is a set A, to a set B, then what exactly am I doing is, let's just say this is my set A, which contains some elements. Let's just say element 1, element 2, element 3, and then we have another set B which has elements such as A, B and C. Then I'm basically under the relation R, I'm relating element from set A to set B. So I'm relating, let's say, 1 to A. So since I've related 1 to A, if I write down the set of relation here like this way, then that will contain an element 1 comma A, which basically means that the element 1 is related to the element A. Similarly, I can have another relation. I can relate 3 to B. So if I'm relating 3 to B, the next element that I'll have here is 3 comma B. So this right here is an example of a relation. Now I can have a different relation. So let's just say I can have name this as R1, and I can write another relation R2 where I'm relating 1 to A, then I'm relating 2 to B, and I'm relating 3 to C. So if you see, this element A is related to A, the element 2 is related to B, and the element 3 is related to C. So I'm relating an element from the set A to a set B. Now the type of relations that we're going to focus on this particular chapter are relations in A. Now what do I mean when I say relations in A? When I say relations in A, that means I have a set A which is, for example, 1, 2 and 3, and I take the same set again, which is the same set A. So I have again 1, 2 and 3, and now I'm relating an element from set A to set A. So this relation R is from set A to set A. That's why it's called a relation in A. Okay, now this type of a relation will look like something like this. We have 1 comma 1, let's just say, then we have 2 comma 2, wherein 2 is related to 2, and we have 3 comma 3. So this is one such relation. I can have another relation, let's just say R2, wherein I'm relating 1 to 3, I'm relating 2 to 1, and I'm relating 3 to 2. So these are the different possible options for a relation that I can have. Okay, now what we're going to do is, if you see, if this is my set A and this is my set A, if I try to write a Cartesian product of this set. Now what is a Cartesian product? In very simple terms, it means that you take all possible combinations. So Cartesian product, it is represented as A cross A. You take all possible combinations. First you take 1 with 1, then you take 1 with 2, then you take 1 with 3, then you take 2 with 1, then you take 2 with 2, then you take 2 with 3, and lastly we'll take 3 with 1, 3 with 2, and 3 with 3. Now if you just look at this thing right here, what we have is, if you see, this is the relation R1 that we have. Now if you see, R1 contains the element 1 1, which belongs to the Cartesian product. We have 2 2, which belongs to the Cartesian product, and we have 3 comma 3, which also belongs to the Cartesian product. So I can simply say that the relation R1, the set of relation R1, is basically a subset of the Cartesian product A cross A. Similarly, if you see here, we have in relation R2, we have elements 1 comma 3, which belongs in the Cartesian product, 2 comma 1, which also belongs in the Cartesian product, 3 comma 2 also belongs here. So this is also a subset of the Cartesian product. So whenever you have two sets, we have a set A and we have a set A, and we are defining a relation R in set A, then any relation that you write in this set, any relation, it will always be a subset of the Cartesian product. This will always be true. Now if we have clearly understood that what a relation really is, now we'll hop on to the different types of relations that we have. So that's the next thing that we are learning. We'll be learning the different types of relations. Now starting, I'll just quickly tell you what are different types we have. Now we have three main categories, which is reflexive, symmetric, and we have transitive. But before going to this three main types, I'm going to quickly go through some of the smaller relation types that we have. The first type of relation that we have is called as an empty relation. Now, from the word itself, it's an empty. Now, remember always, relation is always some set that we are talking about. Because if you see in the previous example, relation R1 that we talked about, it is a set. Relation R2 that we spoke about is also some set containing some elements. So once again, if I'm talking about an empty relation, I'm basically talking about an empty set. So what's an empty relation? A relation R. This is very important. The next thing you have to say, in a set A, you have to be, whenever you're defining a relation, you always have to tell me which set you're defining that relation onto. So this is very important, always telling what is the set A. Now a relation R in set A is called an empty relation. It's called an empty relation if no element in segment of A is related to any element of A. So basically what are we saying? We are saying that there is a set A, let's just say having elements A, B, C, and there is the same set A again having relation A, B and C. Now what are we saying? That there is a relation R such that A is not related to A, or A is not related to B, or A is not related to C, or B is not related, B is not related to B, B is not related to C, nothing. No element in A is related to any element in A. So there is no relation at all. In this case, the relation R, which is a set, is going to be a null set. And once again, null set is always a subset of the Cartesian product. Okay. So this is how we are defining something known as an empty relation. The next type of relation that we have, the second one, is something called as a universal relation. Now, universal relation is the exact opposite. Consider this as your social butterfly. Now, who's a social butterfly? Who's attracted to every single one? In that case, let's just say you consider a set A having elements, let's say 1, 2, and you have the same set A having elements 1 and 2, then here 1 is related to 1, 1 is also related to 2, 2 is related to 1, 2 is also related to 2. So basically, every element of set A is related to every element in set A again. So the definition we're going to write like this way. A relation R in a set A is called a universal relation if each element of A is related to every element of A. So basically you take each and every element of A, you take for example 1 is related to all other elements. 1 is related to 1 is related to 2, if there was one more 3, then 1 will also be related to 3. In this case, your relation R, if you see, if you write the particular elements here, which is basically 1 is related to 1, 1 is also related to 2, 2 is related to 1, 2 is also related to 2. Now don't you think this is as good as writing that this is basically the Cartesian product A cross A? So in this case, for a universal relation, R is basically the Cartesian product. It contains all possible combination of the elements. In the empty set, R is empty, it does not contain any element, there is no relation at all. In universal, every element is related to every other element in A. So these are the two basic types of relations that we have. Now, the next thing that we're going to take is, we're going to take a few examples. We're going to take the next. Now the next thing that we're going to learn, we'll come back to the three main relations that we had. We'll learn what is a reflexive relation. Then we're going to learn what is a symmetric relation, and lastly we're going to learn what is a transitive relation. So we'll first come to reflexive. Now for this, I'll prove it using an example. I'll show you using an example. Now every time whenever you're going to state a relation, what is very important is you tell on which set you are defining that relation. So I'm going to say let a set be A. So I'll take a very easy one. I'll say let set A contain the element 1, 2 and 3. Then what I'm doing is I'm defining a relation R in set A. Okay, so I already have my set A. I have defined my relation R in set A. Now if R contains the elements which are 1, 1, 2 comma 2 and 3 comma 3. So basically what have I done here, I have taken a set A having elements 1, 2 and 3. I have taken the same set A again, which is basically 1, 2 and 3, and what I'm saying here is that 1 is related to 1, 2 is related to 2 and 3 is related to 3. So basically every element here is related to itself, is related to itself. When you have such kind of a thing, you'll say that R is a reflexive relation. So the definition we're going to write: for every A belonging to the set A. So this is my set A, which is the set of the elements onto which I'm defining the relation, and small a here I'm taking any element in set A. Okay, so I'm saying that let for every A belonging to A, what should happen? A comma A should belong to the relation R. For example, if you take the case here, 1 belongs to the set A, 1 comma 1 belongs to the relation R. Then we have 2 belonging to set A, 2 comma 2 belongs to the relation R. Then we have 3 belonging to set A, and we have 3 comma 3 belonging to the relation R. In this case, it is going to be a reflexive relation. Now, let's just say I'll take one more example. I'll take a set B having elements, let's just say 3 and 4 and 5, let's say. Now I'm writing a relation R, which is basically 3 comma 3 and 5 comma 5. Now my question to you is, do you think this relation is reflexive? Well, the answer is no. This is not reflexive, because if you see, B contains an element which is 4, but you don't have 4 comma 4 does not lie in this particular set. It is not present. So since we'll say that 4 belongs to the set B, but what happens? 4 comma 4 does not belong to the relation R. Therefore, R is not reflexive. So what should have, even if one element is not present, it is going to be not reflexive. Okay, so when you want to prove that a set is reflexive or not, very important, you focus on the set that is given to you. You focus on this particular set that is given to you. Now given A and given B, every element in this set has to be related. Every element. Okay. Now if reflexive relation is understood, we're going to go on to the next one, which is called symmetric relation. Now, if I have, once again, for symmetric relation, I'm going to have the set A first. I'll take the very same sets. I'm going to take 1, 2 and 3, and then I'll write a relation R, which is basically, let's just say 1 comma 2 and 2 comma 1. Now comes the question, do you think this is symmetric? Yes, this is symmetric, because if you see, what is the basic condition of symmetric is, if for example 1 comma 2 belongs to 1, so I'll just consider 1 comma 2 belonging to R. The ulta of this, that is 2 comma 1 should also belongs to R. So if you simply interchange the elements here, 2 comma 1 should belong to R, and if it is belonging to R, then we'll say therefore R is symmetric. Okay, so in this case we'll say, if the definition says if A comma B belongs to R, then this implies that B comma A should also belong to R for all A comma B belonging to the set A. Now, one important thing right here is, if you see for reflexive relation that we had learned earlier, I was clearly stating here that this relation right here that we considered, this is not reflexive, simply because of that fact that 4 comma 4 was not belonging to the set or to the relation R. But here if you see, 3 belongs to the relation, 3 belongs to the element set A, but I have not taken 3 as an element in the relation R, but still I am saying that it is reflexive. Now here comes the interesting thing. When you want to show that any set is symmetric, you have to focus only on the given relation. This is not important for us. The given set A is not important. What is only important is the relation. So for example, if I'm writing a set A, which is basically A comma B comma C, and I'm stating a relation R, which is A comma B, B comma A, and I'm saying A comma C. But if you see right here, I have not included C comma A is not there. So since C comma is not there, this is not symmetric. I don't care what the other elements in A, in this element A, set A is. I'm only interested in what are the relations in set R. So if A comma B is there, B comma A have to be there. Similarly, since A comma C is there, here C comma A has to be there for it to be symmetric. So this is the basic things about symmetric. We learned about reflexive. The last type of relation that we're going to learn today is called as the transitive relation. Now, what's a transitive relation? Let's just say if I have a set A, which is basically 1 comma 2 comma 3, and I'm defining a relation R in this particular set, which is basically 1 comma 2, 2 comma 3. Now do you clearly see for this particular elements, if you take these two elements, 2 and 2 is the same. So what are the remaining elements right here? The remaining elements that we are left behind are 1 and 3. So if 1 comma 2 belongs to relation R, 2 comma 3 also belongs to relation R, then if you want this particular relation R to be transitive, then 1 comma 3 have to be there. The moment 1 comma 3 is there, this relation is said to be transitive. Okay, so we'll say if the definition states that if A comma B belongs to the relation R and B comma C also belongs to the relation R. So we can assume that this and this are belonging to the relation, then what should happen? This should implies that A comma C should also belong to the relation R for all A comma B comma C belonging to the set A. Okay, so once again if you see, this does not contain all elements, but we are just taking a sample. So here also we'll focus on the relation R. We are not interested in what are the other sets. There might be some other elements in A, for example, there might be 4, but we are not interested in that. We are only interested in what is the given relation. As long as this rule is obeyed for this particular given relation, we'll say that hence it is transitive. Okay. Now that we have learned about reflexive, symmetric and transitive, lastly we're going to learn about what is an equivalence relation. So what is an equivalence relation? A relation R in a set A is said to be an equivalence relation if R is, so R has to be reflexive, R has to be symmetric, and R has to be transitive. R has to be all three of this, reflexive, symmetric and transitive, for it to be an equivalence relationship. If even one thing is not there, then it is not equivalence relation. So it has to be reflexive, it has to be symmetric, and it has to be transitive for it to be an equivalence relationship. So we'll stop right here for today's class. Thank you so much for attending, and I'll see you in my next class. Please follow our channel, which is Bright Minds Academy Goa. I'm going to posting a lot more Goa board class 12 mathematics videos as well as physics and chemistry videos, and I'll be doing a lot of in-depth tutorials, a lot of paper solving, a lot of this and that. So hopefully I'll see you in my next one. Thank you so much. Bye bye.